Okay, second part of chapter 10 of counting methods or combinatorics is called using the fundamental counting principle. The fundamental counting principle or the product rule. Let me just write it down. Chapter 2. So chapter 10. Okay, section 2. Let me just write point 2. Okay, fundamental counting principle. Okay, or which is the same, is called the product. Okay, the product of multiplication, the product or multiplication rule. Okay, you see, it's product multiplication. It's very simple words, but that one sounds very solid. Fundamental counting principle. So fundamental. If you understand why we have to multiply, it will be just the half of the key to solve very difficult problems. Now, first of all, I have to read on page 4 in the PowerPoint. Okay, the important moments for using fundamental counting principle, and then we start working with special problems, and then I will explain to you how this fundamental. So I formulate it, and then we'll start using it. So what you have to know is to know the meaning of the uniformity in counting and in understanding the fundamental counting principle, the product rule. Now next, what we will learn in the middle of our process, the so-called notion of factorial of a whole number. And then we use, in the end, the number of arrangements, the number of distinguishable arrangements, and okay, so if you have some objects and you have arrangements and distinguishable arrangements. Okay, so now I formulate this principle which you have to learn. Let me just formulate it in here on the right side. Uniformity criterion. Uniformity criterion. Okay, call it fundamental counting principle as abbreviation. It will be FCP. Okay, or multiplication rule. Uniformity criterion of maybe not of four multiple part tasks. Okay, this criterion is uniformity. Uniformity is the key word here. Is a number of choices for any particular part equals the same okay, now the important part, no matter which choices were selected. For previous parts, for the previous parts. Okay, no matter which choices were selected for the previous part. No matter means independently or with no, how to say, connection with the previous part. Now, of course, it depends, but the number of choices. Okay, important thing: the number of choices doesn't depend on which. Okay, so which part you start with and which you continue. Okay, and let me now formulate the fundamental counting principle, which is on the page 6 of the PowerPoint. Fundamental counting principle. And this is just generalization of what I told about tree, about the table, and about okay, 3 problems we solved before. So suppose we have some task consisting, okay, consists of k separate parts. And satisfies how do we write uniformity criteria? Let's write it's UC. And satisfies UC. Uniformity criteria. So next choice, so the number of ways to choose. It doesn't depend on the total on the previous part. So N1 is the number of ways to choose okay, object number 1. N2 is the number of ways, okay, to choose object number 2. Okay, you see subscript means which object you choose. You choose some object and call it 1, choose object, call it 2, and then your n sub 1, n sub 2, and so on. And finally, so n sub 3, the same way n sub 4 and 5. And finally, because we have n sub, we have k of them, k. So the last will be n sub k. And the number n sub k is the number of ways to choose an object number k. Okay, so you have k separate parts, and they satisfy UC. So this is my task. So first I do first task, and I have N1 choices, then N2 second, then and so on. Okay, then total number of ways, okay, to complete the task, total number of ways to complete the task equals the product N1 times N2 times N3 times and so on, and times N sub k. You see in here it's written letter K, capital K, but it means 3 dots, it means and so on. Okay, I taught you during the whole semester that 3 dots means that something is, so this something is hidden here. It's everything is written, and 3 and 4 and 5 and 6, but they are not mentioned because it's too stupid to continue that. So it means that you have to multiply all the numbers. Total number of ways equals the product. Okay, so now we start solving. Okay, problem. Okay, let me just start. Problem number 1. Problem 1. So you have alphabet. Okay, you have digits. 0, 1, 2, 3, 4, 5. We call it alphabet. And A. So this is alphabet. Okay, why I call it alphabet? Because you see, all the digits we use for numbers, for integers, for fractions and so on, are taken from, so 0, 1, 2, 3 up to 9 are taken from the set, from 0 to 9. But these numbers came up after 2000 years from Arab East, and so they were transformed from letters. And letters are characters from an alphabet. That's why I call it alphabet. And this will play the crucial role, that word alphabet, in our consideration in our mathematics, in our mathematical solutions. So alphabet is a set, in this case, 0, 1, 2, 3, 4, and 5. So it means it's, in the terms of the sets, it's a universal set consisting of these 6 objects from 0 to 5. And remember that the order is not important here. It's just a kind of bag, and in this bag you have six characters from 0 to 5. Okay. Now you want to do the following. You find the number of 2-digit integers, AB. So the same problem as before, AB, such that each digit is taken from this alphabet, such that A and B belongs to alphabet A. And question is, standard question is, how many ways to do that? Okay, now we use the fundamental principle. It's a little bit different than here. Here is a table, but I will teach you in a much simpler way, not actually the same way, but I will do not draw the first, do not draw the table. So we have the following reasoning. First digit, second digit. Digit A, digit B. Now, what could be the first possible digit A? Could it be 6? Could it be 5? Yes, it could. Could it be 6? No, because 6 is not here. Could it be 0? This is the question. Can the first digit of a number is 0? For example, you write 06. Is it a 2-digit number? No. Usually 2-digit number is 16, okay, 26, but not 06. It's 1-digit number. We usually do not write 0 in front. So 0 is not here. You can write A is not 0. Okay, so therefore what A could be? A could be either, let's write A belongs to the 1, 2, 3, 4, or 5. Yes? How many possibilities you have? 5 possibilities, 5 ways. So you can start your number with 1 and then extend, then 2 extend, 3 extend, 4 and 5, as we did in the when drawing the tree. Okay, now next we have to extend. Then you take B. B, what could be B? Could be 0? Yes, of course. For example, if you take 3 here and write 0, it will be 30. So 0 could be here, 1 could be here, 2, 3, 4, and 5. How many ways you can choose? Can you choose B? 1, 2, 3, 4, 5, 6. 6 ways. And after that, we apply this principle saying that these 5 ways, okay, each of those corresponds to 6 ways. And therefore we have to add 6 ways for 1, 6 ways for 2, for 3, for 5, for 4, for 5. It will be 6 plus 6 plus 6 plus 6 taken 5 times, which means 5 times 6, so it will be total 30 ways. 30 ways or 30 two-digit numbers. Okay, 30 two-digit numbers. You got it. Let me just draw a tree here. So you start from the point and then you go, okay, 1, 2, 3, 4, and 5. Okay. This is the first digit. Okay, and then after that you have to extend 0. You have to draw 6 segments, 5, 6, and then write, okay, and then write 0, 1, 2, 3, 4, 5. There are leaves growing from 1. And then the same thing is here. Okay, so 1, 2, 3, 4, 5. And likewise here. Okay. And so on. Let me just not draw. So you have 6 extensions of digit 1, 6 extensions of digit 2, and so on. 6 here, 6 here, 6 here. So you take 1, 2, 3, 4, 5 times of 6. And that's why I have 30. Okay, where did you use the uniformity? You got 30, 30. Let's, okay, we can see, so our plan was the following. Plan is as follows. First you choose letter A, and let me just write it as big one, and then we choose letter B. So for example, we choose letter digit 3 and then extend 4. If you take 3, for example, then you can extend 3, 0, 3, 1, 3, 2, 3, 4, and 3, 5. Like here, from 3 you have 6 possibilities. Okay, and that's why you have to take 6 for 3, for the digit 3, 6 for 1, 6 for 2, 6 for 4, 5, so 5 times 6. That's why I multiply. Okay, let's check the other way around. Let me start, again, A is not equal to 0, this is B, and now we start with letter B. So first letter B. So we start from the end. We start from 0. Okay, so what could it be? 0, 1, 2, 3, 4, and 5. We have, okay, this set. We have 6 possibilities. Now we go backwards. 6 possibilities. And for each possibility, how many possibilities do we have for A? 0 we don't have, because the first digit cannot be 0. But we have 1, 2, 3, 4, and 5. We have 5 possibilities. So in this case, we take 5 taken 6 times. Before we had 6 taken 5 times. And now we have to take 6. Okay, so for 0, for example, if you connect with those ones, you get 10, 20, 30, 40, 50. And then 5 of them. Then for next one you have 5, 5, 5, 5, so 6 times. And it will be 6 times 5, the other way around. And the answer will be the same. Okay, this is the uniformity principle, that the number of choices is the same. Let me just mark again, is the same no matter which choice was selected for the previous parts. First we choose first letter, first digit and then second. Or we can choose second digit and then first. And we found we got the same answer, and our plan, you see, our plan is different. In the first time we used 5 ways and then 6. Here we use 6 ways and then 5. But our choice to pick one of those does not depend on what we picked on before. So we pick 4, then we choose again 1, 2, 3, 4, 5. I will show you an example when this principle will be violated, and you will see that uniformity criterion is the most important part. Okay, next problem is counting the number of IDs. Okay, how many ways, so let me just write question. How many ways can you select two letters? Again, this denote this letter small a, small b, meaning that they're letters, followed by 3 digits for an ID. So what is your ID? Let's write. What is your ID? ID is the following. It has 5 positions. Okay, first one is letter. Okay, call it small a and call it letter. Now next is B, is also letter. And then followed I and second letter. Now, and next will be digits. Let's write D1, D2, D3. Okay, all those are digits. Question is how many ways, what is the number of IDs? Okay, let's look. You have to start with what? Okay, let's start from the beginning. First you have to, in the beginning you have to make a plan. Which object you choose first, which object you choose second, and so on. Let's take first letter. We call it small a, but we'll use letters from the alphabet and let them be in the upper case, and so capital letters. So which letter could be taken for the first one? Could be A, B, C, and so on, X, Y, Z, right? This is the set of letters. How many ways? How many letters?
26.
26, good. Okay, so let me, 26. Let's write 26. 26 for A. Next is also letter. And do we have a restriction? No, we don't have. So therefore, for the second letter, we also have 26 possibilities. So if you consider only letters, it will be 26 possibilities for the first letter, 26 for the second, and total, it will be 26 times 26. Imagine that first letter are colored in red, and the second letter colored in green. Then take one red letter and then green letter. So it's kind of 2-digit number, but instead of digits you have letters. Next we go to digits. There is no restrictions as in the previous problem when we consider 2-digit integers. First digit could be, digit could be whatever you want. So it could be 0, 1, 2, and so on up to 9. Anything. How many possibilities?
10.
10, because it's from, by the way, so if you remember the law plus minus 1, which I taught you, it's 9 minus 0, which is 9. Then plus 1 will be 10. So it's 1, 2, 3, 4, 5, and that will be 10. So therefore you have 10 possibilities, 10 ways to choose object number 3. And object number 3 is a digit. So you have 10 possibilities. Okay, the same here, 10 possibilities, and same here, it's 10 possibilities, because there is no restrictions. Total you have, so this could be wrote as follows, 26 squared, because it's taken 2 times. 26 times 26 taken 2 times, 26 squared. And 10 times 10 times 10 is times 10 to the power 3, because there are 3 of them. And the answer is 676,000 IDs. Okay, so we solved a pretty difficult problem, but this is one of the simplest problems in that areas. Okay, I hope you understood the idea, and if you have any questions, please ask. to make some practice, let us solve a little bit different. Okay, one more problem. That's right, question. Okay, you toss 3 dice. 3 dice. Before we consider 2 dice and we draw the table. Now 3 dice. And let's just draw some cubes. And you see on the first one is A, B, and C. Actually, there are digits and you have a 3-digit number. Remember that there is no zeros, so therefore it will be real 3-digit number. So how many? The question is how many? How many 3-digit numbers? Okay, let's look. Okay, we just reserve 3 positions. Okay, we know that the set, okay, our set is 1, 2, 3, 4, 5, and 6. Only those could be outcomes. Okay, so A, B, C. For A, you have 6 possibilities. Okay, and once you toss it, then for the second one you have 6 possibilities. And this you have 6 possibilities as well, and all of them are independent, no matter which choice you take. So if you just toss the second one, it will be 6, and doesn't matter which will toss next one. So the answer is 6 to the power 3, and the answer is 216 outcomes. Okay, so this is the answer, and that number, by the way, is more important. It tells, if you write the answer this way, it tells me how you solved, how you found it. If you make some arithmetic mistake, okay, I will close my eyes for that mistake, but that one is the most important. Okay, so 216 outcomes total. So we answer this question. So that is the answer. Okay. Now, by the way, so the probability that all of those are 6s equals, okay, if here is 6, 6, and 6, it will be one possibility like that out of 216. So probability that A equals B equals C equals 6 equals 1 over 216. 1 over 6 to the power 3. Okay, but this is a different story. Okay, next question. Okay, consider 3-digit numbers. 3-digit. Okay, 3-digit numbers, integers, with the digits okay. Okay, digits are, suppose digits what? 7, 8, and 9. Okay, 7, 8, and 9. Important thing also, another restriction, now I have a restriction. So we have 3-digit number A, B, C. Okay, B is not A, and C is not B, and C is not A. So all the 3 digits are different. It's better to say distinct. Okay, all A, B, C are distinct. So how many such 3-digit numbers? If you consider, if all of them some of them could be equal, then you have 3 possibilities for this, 3 for that, 3 possibilities for that. So total will be 27. But because you have restriction, we have much less. Okay, let's look. Let's start with A. How many possibilities to pick the first digit? Either this or that or that. So 3 possibilities. Got it? 3 possibilities. Either 7 or 8 or 9. Now after that you choose B. B is not equal to A. But we don't know what we have chosen. If we choose 7, then B is not 7, but could be 8 and 9. 2 possibilities. If we choose 8, then B cannot be 8, but 7 and 9 could be taken. Again 2 options. Again 2 possibilities. And if we choose 9, then we have 7 and 8. So therefore this 2 does not depend on, it depends on your choice of A, but the number of those does not depend on the number of choices to choose A. This is exactly uniformity criterion. The number of ways does not depend on the number of ways, doesn't depend on what you choose on the first place. This, the digit itself depends, but the number of ways to choose it doesn't depend. So here we have 2 possibilities. What is 2? Is 3 minus 1. We don't know which one we use here, but we know that it's not equal A, so therefore one of them must be removed. So we have 2 possibilities. And last one is C is not A, and C is not B. So therefore what's left over? Only one possibility, right? For example, if you choose here 8, then you choose say 9, then the only possibility is to choose 7. One possibility. And so the answer will be 3 times 2 times 1. It will be 6. Okay, 6 possibilities, and because it's so small number, we can write all of them. Let's start with 7. Okay, so all the possibilities, all of them. Start with 7. What's next? Could be 8, could be 9. That's it. Right? Now, after that, if you have 7, 8, the only possibility is 9, and here is the only possibility is 8. So, 2 of them. If we start with the digit 7, so we have the first group. Let's start with 8. Next digit could be 7 or could be 9. Cannot be 8. So therefore next will be 9 here and 8, 9 and 7 here. We have the second group starting with 8. So okay, 2 groups. And if you start with 9, the next extension could be 7 or 8. Okay, and therefore the remaining digit is 8 here and 7 here. Third possibility. So you have 3 groups, 1, 2, 3, it's reflected here. The number of choices to pick the first digit, either 7 or 8 or 9. 3 possibilities, 3 groups. Second, 2. You have next you have 2 possibilities, but we don't know here. We don't know exactly what. For 7 we choose 8 and 9, for 8, 7 and 9, and for 9, 7 and 8. But each time we choose 2 of them. That's why it's written 2. And once those 2 digits are chosen, the remaining number could be chosen in exactly one way. So multiplied by 6. Okay, now I pronounce a very important words, and we'll go to the next, we'll make next step. So this number, the product 3 times 2 times 1, for the brevity is denoted as follows: 3, and then you write exclamation sign. And it's pronounced 3 factorial. 3 factorial. 3 factorial. So 3 factorial is just the product starting from this number and up to 1. Okay, now we go to the factorials, and I give you a definition, and we'll make some simple examples. Okay, Okay, I think it's clear so far. I consider the simplest possible examples and apply the product rule. You understand why the product? Because all the time we just multiply the number of ways, and everything is homogeneous. Homogeneity is the same as uniformity. It's another word for, it's another synonym for the uniformity, homogeneity. Okay, so now we go to factorial. Factorials. Okay, so first, first I explain it's an arithmetical way, and then we start applying it. So what is n factorial? So n some number, and it's just a shortcut, it's just a symbol together with the exclamation sign. Don't say please n, it's n factorial. Okay, don't say 3, it's 3 factorial. You have to pronounce 2 words. What is that? So first you take n, then multiply by number 1 less of that, minus 1. Then take next number, n minus 2, then multiply, so n minus 3, okay, and so on. And finally you have to multiply by 4, by 3, by 2, and by 1. So all the numbers from n up to 1. Important thing that if n, so I wrote here 4, 3 to 1, but sometimes 4 is not participated. It's not used here. Okay, let's calculate some numbers. So first of all, and this is the definition. Okay, you must remember that. Definition of 0 factorial. If you put 0 here, 0 factorial, 0 times negative 1, negative 2, negative 3, it doesn't make sense. All the numbers must be positive. So therefore, for 0 factorial, we have to give a special definition. Okay, remember that 0 factorial is just 1. It doesn't, doesn't satisfy the common rule. Okay, this is general definition, and that one in particular, which you will see is useful for calculation. Now let's write different primes, different factorials for different numbers. So start with 1 factorial. What is that? You have to take, if you use this formula, you have to write 1 and then multiply by 0, but 0 is not positive. So therefore, the only what you can take is just that 1, the less number 1 in here. Actually, I would say maybe it's better to go backwards and write 1 times 2 times 3 up to n. So go this way. In which case you will know where you have to stop. If you start with 1, so n is already 1, so you do not need to go to the second step. It will be just 1. Now let's calculate 2 factorial. It's, let's just write 1 times 2. And 3 is not here. So therefore the answer is 2. Let me circle. Yeah. So far small numbers. Now 3 factorial. It's 1 times 2 times 3, or 3 times 2 times 1 is 3. And we just calculated that. This is just 6, also small number. 4 factorial. You have to take, let me just write now in the normal way. So you start from 4 and end with 1. 4, 3 to 1. Then multiply 4 times 3, 12, times 2, 24, times 1 is 24. Let me notice here immediately that 4 factorial can be obtained from 3 factorial as follows. You take, okay, you do the following. If you write parentheses here, you will see 3 factorial here. 3 times 2 times 1, 1 times 2 times 3. 3 times 2 times 1 is 3 factorial. and then we multiply by 4. So it's 4 times 3 factorial. Okay, I ask you to write the factorial when you use multiplication in parentheses. Otherwise, it's just one symbol, one number. If you don't write parentheses, you'll make mistake. It's 4 times 3 factorial. Now, then the answer is 24. What is 5 factorial? It's 4, 3, no, sorry, start with 5. 5, 4, 3, 2, 1. Okay, remember, you multiply them, not add, like we did this in the first part of our course, when we found the sum of arithmetic progression. Okay, so how to find that? I will write the answer a little bit later, but if I put parentheses here, okay, that number is 4 factorial. So therefore the answer is 5 times 4 factorial. So if you multiply, so what you have to do, 5 multiplied by the previous number, by 24. And the answer is 120. Okay, let me calculate up to 10. So 6 factorial, one more time. I will repeat what is that, and then we'll just simplify that. So you have 6, 5, 4, 3, 2, and 1. And if you write parentheses here, it's the same as 6 times 5 factorial from the previous one. 5 factorial is the same as that product. But 5 factorial is already counted. It's 120. So 6 times 120, and the answer is 720. Now you understand what you have to do for 7 factorial. You have to take 7 and multiply by the previous number, 720. Let me just write down. 7 factorial equals, it's 7 times 6 factorial. It's 7 times 720, and the answer is 5040. Okay, 8 factorial is 8 times 7 factorial, which is 8 times 5040. So the answer is, 8 times 40, it will be 320. 5 times 8 is 40, so you have that number. 9 factorial, let me just separate. 9 factorial, 9 times 8 factorial. 9 times 40,320, and the answer is 362,880. That number. And finally, 10 factorial, it's 10 times 9 factorial. So when you multiply by 10, you just write 1 0 in the end. So you have to take this number, 362,880, and write one more 0. And then write comma if you want here. 3,628,800. Okay, now if you look at the numbers, they are very small numbers in the beginning. Only you have first jumped from 6 to 24, then suddenly you jump to 120, then 720. Okay, the ratio becomes, this to that becomes bigger and bigger. Then 5,040, then 40,000 something, then 362,000, almost 363,000, and then 3 million and more than 3.5 million. So this number grows very fast, so it's a kind of exponential. And there is a formula for that. In mathematics, it's called Stirling formula, which I don't want to write it down. I don't want you confused here. Okay, so now a little bit more with arithmetic. So there are some examples. There are some examples in the book. Yeah, by the way, again, it's written factorial formula here, and it's written letter K capital. Actually, it should be written 3 dots, which means and so on. So the product of all the numbers from n to 1. Okay, so there's 3 simple examples, and I show you a little bit more. Okay, first example. 4 factorial. We already calculated. 4, 3 to 1 is 24. B. 4 minus 1 factorial. Okay. It's not 4 factorial minus 1 factorial. First we have to subtract what's written in parentheses. And that's why I ask you to write parentheses as much as you can. Otherwise you will make a mistake. So actually this is 3 factorial. And the answer is 6. Okay, and last example here is 5 factorial over 3 factorial. If you erase, if you cross, so if you cross the fraction like factorial, factorial, you get 5/3, which is absolutely not true. Once, if you erase factorials and got 5/3, you'll get an F immediately. It's not true. So it's not 5/3. What is that? 5 factorial over 3 factorial. And also let me show you that you do not need to make all the multiplications. See, the numbers become bigger and bigger. If you calculate a number and then divide by another number, you'll get the correct answer if you use calculator. But without calculator, use the rule I taught you many times. Split into factors and then cross and then reduce the fraction. What is here? It's 5 times 4 times 3 times 2 times 1. What is 3 factorial? It's 3 times 2 times 1. And you see that 3 times 2 times 1 is the same number. So cross it. What do you have? After that you rewrite 5 times 4, and the answer is 20. You got it, first reduce and then multiply. Okay, now I show you my own example. Okay, next page tells you that 0 factorial is equal to 1. Please remember that. Okay, I'll show you my own example. So for example, what is 10 factorial divided by 9? Okay, who could tell me? What is the answer? Look here at the table.
10?
10, good. So how to solve it? So 10, so you know that here you see 9 factorial is below, but 10 factorial is the same as 10 times 9 factorial. And divide by 9 factorial. So this cancels out and the answer is 10. Of course you can roll that 3,628,800 divided by this one, but if you know the rule, how you arrange this 10 factorial, we just took the previous number and multiplied by 10, which means added 10 on the right. So the answer is 10. Now what is the, what is the answer? 10 factorial over 8 factorial times 2 factorial. You see here, let me just write parentheses. Okay, so what is that? If you write 10 divided by 16, it's incorrect. So what do you have to write? Look, which number is the largest here, 8 and 2? 8 is the largest. So you write the following, 10 times 9 times, after that what you have to write? 8, 7, 6, 5 and so on up to 1, which is 8 factorial. The same here, okay, so you see, if you see 8 factorial here, then you have to stop on this 8 factorial. Okay, below is 8 factorial, and 2 factorial is 2 times 1. Okay, remember that 2 factorial is just 2. You don't need to write 2 times 1. It's just 2. Okay, so you cross those, and remember that you see, what is 8 factorial? It's a huge number. If you write this number and start multiplying, you'll get even your calculator will not help you. But if you do this way, you'll get very simple answer. Now, 2 and 10 gives you 5. So the answer is 5 times 9, and the answer is 45. Okay, some more examples. Yes, you have to have practice with the, just play a little bit with factorials. Okay, let's calculate, say, 100 factorial. You see, 100 factorial is a huge number. It's okay, 30 digits, 40 digits, I don't know exactly. Okay, let's divide by 97 factorial, okay, times 3 factorial. Okay, what is that? Let's solve it the same way. So what you have to do, you have to write the product of all 100 numbers, starting from 100 and ending with 1. So let's start doing this. 100 times 99 times 98 times, and then 97, 96, and so on. If you multiply it starting from 97 up to the end, you'll get 97 factorial. You got it? This is 97 times 96, 95, times 3, 2, 1. Instead of that, I just use this short notation. Okay, here we have 97 factorial. Why did I do this? Because I saw 97 factorial in the denominator, and I have a chance to get rid of this immediately. Times 3, 2, and 1. Okay, I also don't want to write 6. Okay, now you see 97 factorial cancelled out. Okay, this cancelled out. Okay, what else could you cancel? So you see that it's better to leave 100 because it's only 2 zeros in the end. Okay, 3 and 99, you have 33, and 2 and 98, will give you 49. Okay, so now you can mix everything up, so please circle the numbers to see them clearly. And what you get, let me rewrite in a different way. 33 times 49 and times 100 equals, yeah, okay. This time, actually, you can do this. I could show you in column, but let me calculate. Calculate in calculator. So 33 times 49. It will be 1617, and then 2 zeros. Yeah, 1617 and 2 zeros. Okay, so that is the ratio. If you use the huge numbers for 100, so I bet that no matter which calculator you have, and even computer, 100, you'll get an error in your calculation. So you have to use that way. Okay, now look what I wrote here and what I wrote there. 97 and 3 together gives you 100. Here is 8 plus 2 gives you 10. And so if you have such a combination of factorials, it can be written as follows. You write 10, and below you write 97. So not 10, 100. Or you can write 100 and you write 3. And if you know 97, then the other number will be 3 factorial. And if you have 3, then it will be 3 factorial, then 97. By the way, so this one is equal to 100 factorial divided by 3 factorial times 97 factorial. So I changed the factors here, and so my fraction didn't change. So that's why 100 it pronounced as follows: 100 choose 97, 100 choose 3. And here is the same thing. It's 10 choose 8. It depends what you write first. 8. 10 choose 8. Or if you exchange those, it will be 10 choose 2. Okay, in the book, that notation is not used, but you have to know that notation. The notation is as follows: C, choose, okay, 10 on the left side and 2 on the right side. Choose 2 out of 10. And this is the same as from 10 you choose 8. Likewise here is choose from 100, you choose 97, which is the same as from 100 choose 3. Okay, so with factorials we worked. Okay, now important thing, why we use factorials. Okay, remember factorials is the product of all the numbers. Now I erase everything and I ask a combinatorial problem whose solution will be exactly n factorial. So here is the problem. Okay, once you know how to work, now you have to understand the meaning of factorial, the meaning, the real essence of that. Okay, so what's written here on page 14? It's written, when finding the total number of ways to arrange a given number of distinct objects, we can use factorial. Okay, so let's solve the following problem. Okay, I call it question. Number of ways to arrange the 4 marbles enumerated, 4 marbles, A, B, C, D. Number of ways to arrange the 4 marbles, to arrange maybe just in one line, 4 marbles. So the question is, what you have to do? You have to write A, B, C, D, or you can write A, B, D, C, or you can write A, C, B, D, or A, C, D, B. Okay, and so on. And finally, you'll get D, C, B, A. Okay, so if you write all possibilities, then the question is how many? How many of those? Okay, so the problem can be solved using the FCP, the fundamental counting principle or multiplication rule. So what do? You have 4 positions. Okay, okay, let me just write first, okay, second, third, and fourth. Okay, so you pick one of them. So suppose A. Okay, what do? You pick one of these letters, which means one of the marbles, and put it in here. It doesn't matter where you put it. Okay, so third position could be considered as the first one, but you have to make a plan. Plan is just, you have to say, this is my first position, then I do, after my first step, I do second step, and so on. What's my first step? My first step is to choose one of these letters. 4 possibilities. Either A, or B, or C, or D. Right? But second step depends on what you pick. So if you pick A, then A cannot be here anymore. And only B, C, D. How many could be? 3. If you pick B, then the other could be A, C, D. Different ones. If you pick C, it will be A, B, D. One, either A or B or D. If you pick D, it will be one of A, B, C. The number of those will be 3 all the time, no matter which letter, which marble is taken here. 3 possibilities. And this is the uniformity criterion. The number of ways to choose. So let me just write. So first one and second one is not equal to first one. So therefore your alphabet here 4 letters, and this will be only 3 letters, but you don't know which one. It depends on which letter you took on the previous step. But you know the 3 of them. It doesn't depend on what you pick, the 3 will be the same. After that, when you take the third letter, it's not equal to the first and not equal to the second. You have only 2 possibilities. And after that, once, say, letters A, C, D are chosen, then B will be the last one, and there's only one choice to choose. So therefore, using the fundamental principle, you have to multiply those, and the answer is 4 factorial. So 4 factorial ways to choose, to arrange in one line, okay, to arrange of 4 marbles. If you have 5 of them, it will be 5, 4, 3, 2, 1. So therefore, number of ways to arrange n, and now it's important word, distinct objects, not necessarily marbles, could be digits, could be letters, could be whatever you want. Objects is n factorial, which is n times n minus 1, and so on up to 1. So please, okay, so important thing is distinct. Why I say distinct? Imagine that all marbles are white and undistinguishable. Then how many ways you can arrange them? Only one way. No matter how you put, all of them will be white and that's it. But if all of them are distinct, then the reasoning is as follows. On the first position, I use n of them. After that, I have only n minus 1 choices, then n minus 2, and so on up to 1. So I have to multiply them, and by definition, this will be n factorial. So on page 15 is written the total number of different ways to arrange n distinct objects is n factorial. So the word distinct should be underscored here, like I did. Important thing is n factorial. So next question is, how many ways can you line up 6 different books on a shelf? Number of ways to line up. Okay, 6 different. Okay, different is the same word as distinct. Okay, just as synonyms. Okay, to line up 6 different books on a shelf. So if you forget about n factorial right now, so actually the answer is 6 factorial, which is 720. 6 factorial, sorry. 6 factorial, 720. If you forget about factorial, you can make this reasoning. So the first book I put in 6 possible ways, right? Next one only in 5 different ways. Then 4, 3, 2, 1, so I have to multiply them. It will be 728 ways. Okay, now we have to make some interruption here, and now I will explain to you the most difficult moment in this chapter. When you have distinguishable, distinguishable objects, and let me explain to you in a simple way. Okay. Again, I use marbles, and I will use a little bit more complicated problem, and if you understand this problem, then you will understand n choose k of that symbol, and the idea, the general idea. Okay, so let me just write problem. Okay. This problem is my own problem, and after that the solution, general solution, is given on page 17. But you will not understand it unless I'll explain to you how to solve this problem. So you have, you have 15 marbles. You have 15 marbles. So let me just think a little bit. 9, 4, 9, okay, so 10. Okay, 10 white, 3 red. I just write W, white, 3 red, and how are left over 2, right? And 2, say, blue. So the number of ways to line up equals, okay, question. So what's the difference between this problem and the previous problem with 6 different books or n distinct objects? The problem is that when you have white marbles of the same size, okay, that's what I consider. If you have white marbles, if I exchange them, you will have the same arrangement. And that's why several look like different arrangements will be the same. Okay, so let's put 15 marbles. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this, 6, 8, 9, 10. Okay, 10 of them. Okay, 10 of them. Next you have 3 red. 1, 2, 3. Okay, fold, maybe this way. Let's write R inside it. And the other 2 are blue. 2 blue, yeah. Okay, and now after that you start to arrange them. Okay, so how many ways could you do this? So suppose they're located in that way. If you rearrange these white marbles, you'll have the same arrangement. You cannot distinguish. If I exchange this marble with that marble and this with that, you will not find them different. So therefore, you have to solve this problem as follows. First give all the 15 marbles the label. So let's denote them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just for a while. And then we erase them. 10. And here I just write also start all over again. 1, 2, 3. They are red, so I can distinguish red from white. And I write the numbers, so I don't know what I can distinguish between them, and just if they are red, the numbers. Let's use 1, 2, 3 again. And here I use 1 and 2. Okay, so now I have 15 different objects. I can distinguish them. Or maybe, maybe I just write. So 10, 11, 12, 13, okay, 14, 15. Okay, it doesn't matter. So you have 15 marbles. And if you have labels, all of them will be distinct. 15 of them, n equals 15. If n equals 15, all of them are distinct. The number of ways to arrange 15 distinct labeled marbles equals 15 factorial. Okay, but now, as I told you twice already, that if you exchange those ones, okay, between them, it will be the same arrangement. You cannot distinguish if it's different. So, therefore, all these arrangements from 1 to 10, I will count many, many times, but it will be the same one arrangement. So therefore, what I have to do, this one arrangement, it will be the same as 10 factorial. If you have the labels, then I have 10 factorial different arrangements. But all of them, actually, if I erase numbers here, they are the same. So therefore, 15 factorial, I must divide by 10 factorial. 10 factorial, I repeated 10 factorial times the same arrangement. 10 factorial times. So therefore, so far, I have 15 factorial and divide by 10 factorial. So therefore, arrangements I have, if I forget the numbers, the labels from 1 to 10. But now you see three red marbles. They are enumerated. That's why you have 3. That's why they are included in 15 factorial. But now, if I rearrange them, it will be 3 factorial different rearrangements. And if I erase the labels, all these 3 factorial, that is 6 rearrangements, are counted as 1. So therefore, I have to divide by 6, which is, okay, let me just try this number. I must divide by 3 factorial if I erase the labels. Now, what happens next? Here I have 2 factorial rearrangement, which is 2. Okay, but if I erase those, BB and the other BB will be the same. So I have to take the whole number and divide by 2 factorial. Okay, so what is that? Let's write this as a fraction. So you have 15 factorial over 10 factorial. Okay, that one. Then I have to divide by 3 factorial. And after that, the whole thing I have to divide by 2 factorial. If it's too complicated, you have to listen to me one time, and after that, understand the general idea, even vaguely, but then you'll understand where the factorials, how factorials play to each other. So what is that? If you calculate the fraction, you have to move the denominator down up here, so down there. So it will be 15 factorial divided by, so 10 factorial multiplied by 3 factorial, and then divided by 2 factorial. And so the answer is 15 factorial, and now I have to take the whole fraction and move it down. And so it will be 10 factorial times 3 factorial times 2 factorial. And so this will be the final, the correct answer. So idea is as follows. If I label all of them, it will be 15 factorial possibilities. But if I erase the labels here, I must divide by 10 factorial. All the 10 factorial possibilities actually is exactly 1. Okay, next one, I have 6 different possibilities, but now they are considered as 1. So I divided by 6. And finally, B and B, there are 2 of them, but if I exchange them, it will be the same thing, so I have to divide by 2. So this will be the answer. And it's called, notation of that is as follows. You have 15, and then below you write 10, 3, 2. So the total sum must be 15, and write the parentheses. This is a standard mathematical notation. Okay, so this is the answer. Okay, this is the, how to say, real mathematical answer. The other part is just purely arithmetic. You have to calculate exactly numbers. So how to do that? You just write 15 times 14 times 13 times 12 times 11. Okay, I erase this part. After that, you see 10 factorial here. So you have to write all the numbers from 10 to 1. So you just write 10 factorial. Divided by 10 factorial. And then 3 factorial, you can write 3 times 2. Okay, times 1. And then 2 factorial is just 2. Actually, by the way, so now 1 you do not need to write if you multiply. So it will be 3 times 2, 10 times 2. Okay, so that number you have to calculate. And you see that 10 factorial and 10 factorial cancelled out. And after that, what do you see? 3 times 2 is 6. And 12 divided by 6 will be 2. And then this 2 and that 2 also cancelled out. What finally you have to get is 15 times 14 times 13. Whatever number it is. Okay, so let's calculate, just in case. Okay, so what you have to do? 15 times 14 times 13. It's 2,730 arrangements. Okay. So now I just write the what's written in here on the page 17. The number of arrangements. Okay, general formula. Number of distinguishable arrangements of n objects. Number of distinguishable. You see, when you exchange those, it will be undistinguishable. But so if you want to see only those who you can distinguish, distinguishable. Arrangements. Okay, the number of distinguishable arrangements is, what do? You take n factorial, okay, you have n objects, and then you divide by the number of factorials of kind of white, red, blue, and so on, whatever color you have. So you have n1 factorial. You see, it's, they do not write even parentheses. Let me just separate them. n2 factorial. Actually, it's better to write parentheses. n3 factorial, and so on up to the last one, n sub k factorial. Okay, and now I just show you one example. Yeah, actually, okay, let's look here. What you have, let's erase this one. Okay, I have 10, okay, 10, okay, I have 8 white marbles, okay, 8 of them. And then I have 2 black ones. And then I rearrange them. So how many ways could I do this? It will be total is 10. 10 factorial divided by 8 factorial, and then 2 factorial. And then we calculated 45. Okay, here you have 97 white marbles. Okay, 97. And then you have 3 black. Okay, 97, and this 3 black. And what's the number of possibilities? 100 factorial divided by 97 divided by, and then by 3. Everything is in the denominator. And the answer is, okay, so what is 161,700 possibilities. My previous example was more complicated because I had 3 different colors. 3. Here I had only 2 different colors, white and black. And here I had 3, white, red, and blue. In this case, Finally, I got 3 different factors corresponding to 10, 3, and 2. Like in general case, and 1, and 2, and 3, and whatever. So the list will be 3. Total sum is 15. Like here, a plus 2 is 10. 97 plus 3 is 10. So if you have 2 factors, it means that you have 2 colors. If you have 3 factors, you have 3 colors, and so on. Let me just solve. Okay, what is better to? Okay, I erase this one. Okay, we're in the end, and I show you maybe 2 or 1 or 2 problems. So the last problem on page 18 is the following. You have the word. Okay, so question is as follows. You have the word initially. Okay, then you rearrange these letters and you got some non-existent words, okay, but some combinations. So how many different arrangements? Equals, okay, we'll write answer here. Okay, let's look. So answer is as follows, how to calculate. How many letters are all together? What is n? Okay, so look, here we have to write n factorial and then factors. So what is n? Let's calculate. 1, 2, 3, 4, 5, 6, 7, 8, 9. So just write 9 factorial. 9 factorial could happen if you label them. 1, say 2, 3, and so on. If you distinguish letter I, say, from this letter I. If you write, say, 1 here and 5 here, then you can distinguish them because they have different subscript. But then you have to erase the label and divide by the number of these rearrangements. So, how many I's do we have? 1, 2, 3, right? So therefore you have to divide by 3 factorial times. How many N's here? 1, that's it. So you write 1 factorial times. Okay, let me just write parentheses to see clearly. Next, I is already counted in here. Next is T. How many T's you have? Oh, also 1. 1 factorial times. How many A's? Also 1 factorial. How many L's? 2 factorial. 2 of them. And how many Y's? 1 factorial. Okay, 1 factorial is 1, so you do not need to count them. And so what do we have? You have 9 times 8, 7, 6, 5, 4, and then you see 3 factorial here, so just write again 3 factorial. Divided by 3 factorial times, and you have 2 factorial, which is just 2. 3 factorial, 3 factorial cancelled out. And what else? And 4 and 2 cancelled out. You have 1 here and 2 here. 2 and 5 gives you 10. So this the product will be 9 times 8 times 7 times 6 and times 10. Okay, so we can calculate. Yeah, 3 factorial. And the answer is written here, 30,240. So that answer and that answer. So final answer. And this is how we found distinguishable words. And in the test, I ask you the following problem. So let's write first the answer here. 30,240. Then circle it. And please write zeros very carefully. Don't mix them with 6 or whatever. And please circle your answer each time when you got it. Question, standard question in all the books and also in the textbook, and I will give you on the test or quiz. You have the state Mississippi. Okay, and then you rearrange the letters. how many different rearrangements you can get. Use the same thing, so you have to calculate the total number of letters will be n factorial, and then how many m's, how many ones, and so on. You see, by the way, in here, 1 factorials are not counted at all, and you can make, you could confuse here. You see, it's written 9 letters total, 9 factorial, 3 i's and 2 l's. And didn't say anything about y, t, and a, but actually for one single letters, you have to use 1 factorial, 2 factorial, 1 factorial, 1 factorial, 1 factorial, all the time what I said, but they are not counted. You see, all of those you do not need necessarily to write, but to understand that from the first time, you have to write them. Actually, it's better to write, in which case you will show to yourself and you show to me that you understand what's going on and how you use the formula, and in this case you will not have a mistake. Okay, section 2 is finished. Thank you.